Thank you for signing up to watch Actionable Big Data Analytics in Healthcare, delivered by Gough as part of the Intel Healthcare Plus webinar series. NHS spending will be £133 billion by 2020, so the potential for the smart use of big data to inform budgeting has now grabbed everyone's attention.
Hi, I'm Gough, the Global Director of Solution Architecture for Intel's Health and Life Sciences team. Today I'm going to talk about big data analytics. We'll discuss the key trends and business challenges that are creating demand for analytics in this industry. I'll also describe real-world use cases and solutions that are being deployed to address them. Here's the current and future state of data in health and life sciences. Today, health and life sciences data is siloed for the most part. Healthcare providers manage and maintain clinical data, governments or payers the claims data, life sciences organizations manage clinical trials data and high-throughput screening libraries, and the consumer, or patient, owns wellness information related to exercise, diet, etc. If the objective is a patient-centered approach, the current model is obviously far from optimal. Integrating data from multiple silos is required for transformative insights and opportunities. Coming up, you'll hear about how a large healthcare provider uses analytics to more accurately predict which patients are at risk to be readmitted to the hospital within 30 days of discharge by combining data from the hospital electronic health record with socioeconomic data from external sources. We need to move to a person or patient-centered model with integrated computing and integrated data, where analytics is built into the patient care workflow as an accepted and required actor. This will lead to better decisions, improved patient experience, improved healthcare outcomes, and reduced cost. Our vision is to extend personalized care to everyone on the planet, where care protocols are customized to a patient's specific medical condition, or more likely a combination of conditions, as well as their genomic profile. A bit later in this session, we'll focus on real-world use cases and how Intel has worked in concert with partners to deliver big data analytics solutions that create customer value and help advance this vision. In addition to traditional data that's available to healthcare organizations through the electronic health record, such as vital signs information, diagnosis, symptoms, these kind of things, there's an increasing and accelerating desire to personalize diagnosis and treatment for patients by also taking their genetic information into account. This is where genome sequencing, or genomics, comes into play. From 2001 to 2016, the cost for whole genome sequencing dropped dramatically to about £847, where it is today. So the cost of sequencing is no longer really a barrier to personalized care or precision medicine. And this is accelerating into clinical settings much faster than anyone anticipated. Examples of this can be found in pharmacogenomics. Dosing of doctor-prescribed drugs, such as Coumadin, is tied to how well a person will metabolize the drug based on their genomic information. Non-invasive prenatal testing is another example. Now with a simple blood test, you can uncover risks of developing conditions, such as Down syndrome or cystic fibrosis. So this is here and growing. With it comes a significant volume of information that'll need to be fused with the more traditional healthcare information, like electronic health record and claims data. The more data you have, the more expensive it is to manage and to store and to process. So volume, both from a scale and cost perspective, is a significant challenge for healthcare providers. I'll draw your attention to the phrase in the graphic, 665 terabytes of data annually. This is the estimated amount of data that an average hospital generated in 2015, but it's only getting larger. It's hard to scale and hard to afford analytic solutions that can process all this data. Now if you consider that a whole genome with all its data is about 1 terabyte in size, you can understand that if one of the typical hospitals mentioned above decides to sequence 1,000 patients in a 1-year period, then their storage would increase by 1,000 terabytes from 665 terabytes to 1,665. Storing and analyzing large volumes of information is a challenge for healthcare providers that will continue to grow. Here we get into the last and probably most important barrier for healthcare organizations, cost. It's very costly to manage, maintain, and scale traditional analytics environments, like a data warehouse. In some cases, we've been told the cost of a data warehouse can be up to 40 or 60,000 pounds per terabyte. An analogy I'd like to highlight here is Red Hat Enterprise Linux. Linux is an open source operating system. It's free. Because it was open source, it didn't really get much adoption in the enterprise compared with incumbents like Microsoft and Oracle. Once Red Hat took that open source, beefed up some of the enterprise features, and provided a constant support model around it, started accelerating very quickly in the enterprise because of the cost benefits, but also because the enterprise requirements were met. The same thing is really happening with big data, where Apache Hadoop, for example, is an open source platform. Companies like Cloudera have now taken that, improved the security, reliability, manageability, and management features, and provided support. And now it too is taking off in a big way in enterprise environments. One of the most compelling reasons is cost. One of the key use cases is data warehouse offload, or ETL offload. ETL stands for extract, transform, and load. Basically, the pre-processing of information can be done far more efficiently and far less expensively on the big data side. So oftentimes you'll see in a data warehouse environment that running a big data Hadoop solution alongside it for that ETL offload can have a dramatic, in some cases multi-million-dollar cost savings for enterprise organizations. One of the key reasons for offload, of course, is cost. It can be much less expensive to process and manage data in that Hadoop environment, rooted in open source, than in the more expensive traditional enterprise data warehouse environment. This is the big data system that many enterprises are deploying, oftentimes in concert with the traditional enterprise data warehouse, as we'll see in a minute. It goes by several different names. You might hear data lake, data reservoir, or data hub. You can see here some of the differentiating characteristics of the platform. I'd like to dive a bit deeper on a few of these. First is the ability to store all data formats. Some of you have likely heard of data being referred to as structured or unstructured. Structured data is typically data that fits well into a traditional relational database like Oracle or Microsoft SQL Server. A database administrator has to define the format that the data will be stored in, called a schema. This makes it challenging or time-consuming to comprehend new data formats. Demographics data from the EMR is a good example of structured data: name, date of birth, gender, home address, etc. Unstructured data is more difficult to store in a relational database in a meaningful way. Some examples might be free-form doctors' or nurses' notes in the EMR, call center logs, or faxes, which are basically just images. The data lake is designed to store all different kinds of data, structured, unstructured, and everything in between. Second, I'd like to touch on scale. The data lake is what we call horizontally scalable. This means the database, typically including both compute and storage, is spread across a group or cluster of servers. When computation or storage demand grows, you simply add more servers to the cluster. This can be less complex than a traditional or vertically scalable system, which usually involves replacing the old database server with a newer, bigger server. This is sometimes called the rip and replace model. So there's several key reasons why enterprises are deploying a data lake alongside an enterprise data warehouse. Overall costs can be reduced, and the customer can realize the strengths of both platforms. So how's a data lake typically deployed? Most enterprise organizations are getting started with big data with a practical phased approach, as opposed to a disruptive rip and replace approach. Here we see a conceptual representation of an enterprise business intelligence architecture. On the left-hand side, we have structured data repositories, such as relational database systems like Oracle or Microsoft SQL Server. This information is periodically processed and pushed into a centralized data warehouse. Different business units within a single enterprise may have their own data warehouse. The enterprise data warehouse is where data is mined and analytics are performed and visualized. You'll note the unstructured data on the left-hand side is unused in this representation. In healthcare, this could be free-form text fields in the EMR, such as doctor's notes for clinical encounters. Now we've added a Hadoop cluster to the BI architecture, deployed right alongside the existing infrastructure. The purpose of Hadoop in this example is to offload ETL, extract, transform, load, for large volumes of unstructured data onto commodity or inexpensive infrastructure, enabling the enterprise to get a more comprehensive view of the data for their analytics tools. For example, extracting value from clinical information currently locked up in doctor's notes. While it'd be possible to do this with a traditional enterprise data warehouse, it'd be extremely expensive to do so. I'd like to take a moment to touch on another global trend that's not only highly relevant for our next example, but also illustrates why healthcare organizations are really investing in analytics solutions. The trend deals with healthcare payment reform, and it's the global shift away from what's typically called fee-for-service, where every procedure, test, and visit is reimbursed by the government or an insurance organization, toward a model where reimbursement is focused on keeping a population of people healthy, and where payments are tied to measurable quality metrics. You can see one example of this here from the UK, focused on 30-day hospital readmissions. If a patient's readmitted to the hospital within 30 days of a planned stay, the Department of Health will not reimburse costs associated with that readmission. This obviously has direct impact on the bottom line and causes hospitals to be more motivated than ever to prevent this from happening. Our next example comes from the United States and a health system named Sutter Health. Sutter wanted to be able to better predict which patients were at high risk for a hospital readmission within 30 days of discharge, as well as which patients were at risk for a longer than expected hospital stay. This proof of concept focused on 3 key conditions: AMI, or heart attack, pneumonia, and congestive heart failure. The solution was based on Cloudera Enterprise, which uses the data lake architecture we just discussed, and open source machine learning libraries that have been tuned for this platform. Sutter was able to consolidate data from multiple different repositories as a starting point, including data from their EMR, called Epic, and very interestingly also included socioeconomic data from outside the health system. An example of this is real estate valuations from a company named Zillow, which publishes an internet accessible API. This data was correlated to the patient's home address and used as a proxy for their economic situation. The team used machine learning algorithms to create a predictive model. So this is an example of predictive analytics. The light blue bars in the graph show a random sample of patients from the EMR and readmission rates for the 3 conditions I mentioned. The predictive model that the team created with the Cloudera solution are represented by the dark blue bars. This enabled Sutter to identify a cohort of patients that were at high risk for a readmission. Now, higher touch resources, such as a care manager or remote patient monitoring plan, can be applied to these patients to help reduce readmission rates. The POC was successful, not only because of the results generated by the predictive model, but also for demonstrating a cost-effective data lake architecture that can help the organization address the challenge of data silos. I'd like to shift gears and talk about a different type of big data solution. This solution from SAP, Dell, and Intel, called the SAP Connected Health Platform, is an in-memory solution based on the SAP HANA in-memory database. So what does in-memory mean? Essentially, it means that instead of storing the database on disk, it's stored in much higher performing system memory. SAP HANA has been optimized for this model and has also been optimized to run as fast as possible on the underlying Intel CPUs, as our architects have been collaborating directly with SAP on software optimization for over a decade. So why do customers need the query performance that the SAP Connected Health Platform can deliver? Earlier in the presentation, I talked about how data is currently siloed in the healthcare industry. Now that we have some tools that can help break down these silos, such as the data lake. However, as more and more streams of data are integrated, the analytics become more complex and more performance sensitive. The Connected Health Platform can combine these streams, such as provider data from the EMR, omics data, for example, the variants that describe unique characteristics of a tumor, and IoT data from wearables and medical devices, and operate in this combined data set directly in system memory with amazing performance. The Dell Global SAP Center of Excellence is based near SAP headquarters in Waldorf, Germany. They offer great resources to help healthcare organizations speed time to value for their analytics projects. I'd like to end this session with a subsection focused on genomics. Genomics starts with sequencing. Sequencing is the process that determines the order of the DNA nucleotides or bases, the order of the A's, C's, G's, and T's that make up our DNA. As I mentioned previously, the cost of sequencing has dropped dramatically in recent years, accelerating deployment of genomic solutions. The examples I'll provide in this section concentrate on the downstream analysis of this information. This is where the genome is reconstructed from the read information off the sequencer, compared against a reference genome, and the variants are mapped. This determines what's different about the patient as an individual, or how their tumor genome differs from their normal DNA. This analysis lends itself very well to parallelization, and consequently a multi-core, multi-processor infrastructure that can process, store, and manage a massive volume of data. Intel has defined a high-performance computing, or HPC, framework that lends itself very well to genomics, called the Scalable System Framework. And we're working across many OEM partners to deliver solutions based on this. Scalable System Framework, or SSF, is very much focused on balanced system performance across many different system elements, such as compute, networking, storage, fabric, and optimized software. You can see some of the underlying capabilities listed here. Why is it important to customers to balance the system across all these elements? We'll discuss an example with a company called QIAGEN. QIAGEN Bioinformatics is the largest commercial software vendor for genome analysis. High-volume genome sequencing generates an enormous amount of data that must be analyzed as fast as it's produced. Assuming 700 gigabytes of data for a whole human genome, keeping pace with high-end next-gen sequencing system could require analyzing more than 30 terabytes of data per day. According to Illumina, which manufactures the industry's highest throughput system to date, it would take an 85-node high-performance computing cluster to meet these heavy processing requirements. QIAGEN, working with Intel, has created a more cost-effective alternative. Together, the two companies developed a 35-node reference architecture that could meet these same throughput requirements, while dramatically reducing space, energy, infrastructure, and management costs. Based on the performance tests and total cost of ownership analysis, this reference architecture could potentially reduce annual costs by as much as £950,000 from the 85-node cluster defined by Illumina, while delivering the same level of throughput. Depending on sequencing volumes and data center efficiency, this solution could enable full analysis of whole human genomes for as little as £16 each. That's it. Hopefully you've expanded your horizons related to big data analytics, the key motivations influencing customer purchase decisions, and some of the solutions and vendors related to data lake, in-memory, and high-performance computing solutions being deployed by health and life sciences organizations to address industry business problems. Thanks for your time, and have a great day. To find out more about how Intel can help you provide personal healthcare solutions, please sign up to the other videos within the Ingram Intel Healthcare Plus campaign. Enabling mobility and collaboration for healthcare. Intel Healthcare, making it personal. The future of healthcare technology, and breach security solutions for healthcare.